Okay, good afternoon. What we have discussed last lecture, we have studied some of the VLDL programs for the comparator, multiplexer, and flip-flops. Right. Now, in today's lecture, we are going to discuss VLDL program for the some complex circuits such as 4-bit shift register, then arithmetic and logical unit. Right. So that part we are going to cover in today's lecture. Okay. Now we will start with the first part, that is 4-bit shift register. Am I audible?
Yes, sir.
Okay. Now this is a block diagram for the 4-bit shift register. Now tell me, what are different types of shift register do you have? What are different types of shift registers that you have seen?
Serial in, serial out,
Very right. Just put the serial in, serial out. Then
parallel in, parallel out,
parallel in, parallel out. Very right.
serial in, parallel out,
Serial in, parallel out. Okay, where input is a serial and you are taking the output parallelly. That is also correct. Serial in, parallel out. And last one,
parallel in, serial out,
parallel in, serial out. Very right. Input you can take parallelly, output will produce serially. So these are the main four types of the shift registers that we have seen. Okay. Now, can anyone tell the block diagram you are getting on my screen, which type of shift register it is?
Serial in, serial out.
Very right, very right. It is serial in, serial out type of shift register. That means you are applying serial input and also at the output side you are taking the serial output, right? You're not taking the output parallelly. That means from each and every flip-flop, if you take output simultaneously, so that will be the parallel output shift register. But no, from the last one, we are taking the output or we are getting the output. So that is what serial in, serial out type of shift register. Now, so now, as we mentioned, there are four types of shift registers: serial in, serial out, serial in, parallel in, parallel out, and parallel in, serial out. Now, we will discuss here only two types, that is parallel in, parallel out type, and next one is serial in, parallel out shift register. Okay, you can have a VHDL code for serial in, serial out, then parallel in, serial out, or serial in, parallel out. No problem, you can have that. But here for the example purpose, we will discuss only two types, that is parallel in, parallel out, and serial in, parallel out shift register. Now this is the VHDL code for parallel in, parallel out shift register. Okay, as the name indicates, what do you mean by parallel in, parallel out? The inputs are coming inside parallelly and outputs are getting outside also simultaneously. Means if you consider the same block diagram of that D flip-flop, for each D flip-flop input is coming simultaneously, or each D flip-flop input is each D flip flop will receive input simultaneously, and each D flip flop on a clock pulse it will produce output also simultaneously. So that is parallel in, parallel out shift register. So this is the VHDL code for parallel in, parallel out shift register. In this, of course, first part is library. So this is library part. Library IEEE. This is library we are using. In that library, we are using library.package.its item. That means first we have defined the library. Now in that library, which package has to we are using? So this standard logic 1164. This is the package, and in that package, which items we are using? All items we are using. So use IEEE. That means this library we have to use. In that library, this package we have to use, and last in that package, these all items we have to use. So this is about the library section. Then after library section, which part we have to include in our VHDL code? That is entity part. So this is entity part. What we have written in entity? We have to mention the inputs and outputs required for the design. So that part we have to include in entity. Now the entity PIPO, that is parallel in, parallel out. This name I have given. You can give any name. Then port, then clock, D and Q. These three pins we require. So in that, clock and the D are the input pins, and Q is the output pin. Now D is a 4-bit, that means 3 down to 0, that is 4-bit, and Q is of also 4-bit, because input we are getting parallelly, right? Input we are receiving parallelly. That means 4-bit we have to receive simultaneously into the D flip flop, and along with the clock pulse, again we have to produce the output simultaneously from each flip flop. So we require a 4-bit input and 4-bit output. So this is about the PIPO, parallel in, parallel out entity. Now we will talk about the architecture part. Now simply again we have used the process here. That means this is a behavioral type of modeling. Then architecture, arc of entity. What entity I have written here? The same entity you have to use here also. The same entity name it will get here. So this is about the architecture name. Architecture of this entity is begin, process. Now everything is depend upon the clock. Means what? At each clock pulse, the status of the flip flop is going to change. That means at each clock pulse, whenever you apply a clock, the status of the flip flop will going to change. That means after every clock trigger, it will receive the new input, and it will produce the whatever the before previous input, it will produce to the output, and it will receive the new input. This is how the parallel in, parallel out shift register will work. It will shift the current state, and it will receive the new state. So this is how it will work. So after begin, if clock tick event and clock is equal to 1, means if when the clock will get 1 value, means clock will go to the high state or trigger state. Then what will happen? Then Q will get the value of D. This is the simple program for the parallel in, parallel out. That means Q will receive the value of D. That means whatever the current state of flip flop will reflect to the output side, and simultaneously the new state will get loaded into the flip flop, and the new input will get received by the flip flop. So this is how this parallel in, parallel out flip flop will shift register will work. So this is a simple program for PIPO, parallel in, parallel out. If clock tick event and clock is equal to 1, means when you trigger the clock pulse, then what happens? Simply the whatever the current state of D will get received or will be appeared at the output, will get appeared at output side, and output we have defined by the Q. So we have to write here the output variable Q, and D is the input, that means the current state of flip-flop, D flip-flop, and after clock trigger, it will get reflected at the output side. So this is a very simple program for the parallel in, parallel out shift register. Now we will discuss serial in, parallel out shift register. So again, this is library, this is package, and this is items in that package. So you have to remember this type. Then entity we have to define. So again, we will require a clock and clear pin, then input data and output data. So these three input, clock, clear, and input data is a three input pins we require, and Q is the output pin that we require. So in entity we have defined that. Now we will talk about the architecture part. Now architecture of the serial in, parallel out, serial in, parallel out is, again everything will depend upon the clock process. So we have defined here the process clock, then begin, then if clear is equal to 1, then Q will get receive value all 0, means we have cleared all flip flop, right? We have cleared the all flip flop, and at the output side nothing you will receive, only you will receive the all zeros, because it is a parallel out. Output we are receiving parallelly, output we are getting parallelly, but each flip flop will receive input serially only. Step by step it will get it will receive the input, but when the clock pulse will get triggered, it has to produce the output simultaneously. It has to produce the output simultaneously, that means parallelly. Now again we will put the another condition. If clear is equal to 1, then Q will get this value. Else if clock tick event and clock will happen, then Q 3 down to 1 will get received Q 2 down to 0, and of course Q 0 will get received input data. That means we are shifting the bit, we are shifting the data of the previous flip flop into the next flip flop, right? This Q3 down to 0 means it's the Q3 down to 1 means it's the third flip flop that will receive the data from the second flip flop, and the second flip flop will receive the input data. So whatever we have given, first flip flop will receive the input data, second flip flop will get it will receive the data from the first flip flop, and it will transfer the second data to the third flip flop. Means serially we are passing the data from one flip flop to another flip flop. म्हणजे पहिल्याचा दुसऱ्यामध्ये, दुसऱ्याचा तिसऱ्यामध्ये, तिसऱ्याचा चौथ्यामध्ये. Likewise we will transfer data. So this is the last flip flop. Last flip flop will get data of the third flip flop, and this Q0 initial flip flop will get data of the input from the user. So this is the first flip flop, this is the third flip flop, and this is the last flip flop, right? Whatever the data we are of the third flip flop will get transferred to the last flip flop, that is fourth one, right? D flip flop is the last one, fourth one, and at the first flip flop, that is Q0, we will apply the input data, that means user data. So this is how the serial in, parallel out data will work. This is how the serial in, parallel out shift register will work, and this is a simple program for serial in, parallel out shift register. Clear with this? That means at a time we are moving the first 3 bit. That means see here, I will elaborate with the help of this block diagram. Okay, consider this is a serial in and parallel out we are taking from this side. Then what happens? The data of the first flip flop will get received by the user only. That means user data will enter into this flip flop, but the data of this and this will get transferred automatically, or will get shift to the output parallelly, and of course from first flip flop also we will get the parallel output. That means we are shifting the first data of the first flip flop, we are shifting to the next to the next, and this to the next. That's why we have in a code we have written here the Q of 3 down to 1. That means only 3 bits we are considering, right? Q 3 down to 1. That means data of the second, third, and fourth flip flop, right? And will get Q 2 down to 0. That means it will get shifted by the first, second, and third. म्हणजे पहिल्या, दुसऱ्या, तिसऱ्याचा डेटा हा दुसऱ्या, तिसऱ्या, चौथ्यामध्ये आपण शिफ्ट केला. एक एक बिटनी शिफ्ट केला. म्हणजे पहिल्या, दुसऱ्या, तिसऱ्या फ्लिप फ्लॉप मधला डेटा आपण दुसऱ्या, तिसऱ्या आणि चौथ्यामध्ये शिफ्ट केला आणि पहिल्या फ्लिप फ्लॉप मध्ये आपण इनपुट डेटा घेतला. 1 bit we have shifted towards the 1 bit we have shifted with the increment of 1 flip flop, and the first flip flop will receive the input data. First flip flop will receive the input data, and of course if clear is 1, then this condition will happen. Else if means if clear is not 1, then Q will get value of these data. That means data of the first, second, third will get shifted to the second, third, fourth, and first flip flop will receive the input data. That means first bit of the next bit of the input. That is we are applying serially. म्हणजे लक्षात आले, पहिल्या, दुसऱ्या, तिसऱ्याचा डेटा आपण दुसऱ्या, तिसऱ्या, चौथ्यामध्ये शिफ्ट केला. पहिल्या आणि पहिल्या फ्लिप फ्लॉप मध्ये आपण नेक्स्ट बीट घेतलं, and that will be transferred at output side parallelly with the trigger of clock pulse. So this is how SIPO, that is serial in parallel out shift register, works, and this is what the VHDL code for serial in parallel out shift register. All of you clear with this? All of you clear with this? Okay. Now next part that we will discuss is also one of again complex sequential circuit, that is up down counter, right? Up down counter. Now can you have up counter separately, can you have down counter separately, and can you have up down counter? नुसता up counter असतो का? Yes, you can design only up counter. Can you design only down counter? Answer is yes, you can design down counter, and you can design up down counter combinedly also with the help of that mode select pin. That means this mode will decide whether it is a up counter or down counter, and rest operation is same. Now we will discuss the VHDL code for this up down counter. Now this is a VHDL code for this up down counter. So this is the library part. Okay, we have used this IEEE library. In that standard logic .1164.all, this package we have used. Standard logic underscore arith, this package also we have used, and standard logic underscore unsigned, this package also we have used, and in that package we have used the all items. So that's why all we have written. We have used the all items. This is the library part. Then this is the entity part. Num, clock, load, std underscore logic, comma reset, and direction. So these are the input ports that we require. Num is for the number, right? Num is for the number. Then clock is to provide the clock pulses. Then load is to load the data. Reset will reset the counter, right? It will reset the counter. And direction, whether it has to whether it has to behave as an up counter or down counter. So this direction that you can decide. And of course the last pin is output pin. From this port you will receive the output data. So this is the entity for up down counter. Now this is the architecture part, right? So this is counter. We have defined the architecture. Then standard logic vector 3 down to 0. So in this we have defined one signal also, signal temp, and we have it is of class standard logic vector and of standard logic vector 3 down to 0. That means it is 4-bit standard logic vector, right? And signal name is temp. So this signal we have defined. Then begin. After begin, process, clock and reset. All process of this up down counter is depend upon the clock and reset pins. So in process we have written the clock and reset pin. Now again after process begin, if reset is equal to 1, that means if you have triggered the reset pin, then temp, that means this temporary signal will get value 0000. That means 4 times 0 because you have reset the circuit. Else if clock tick event and clock is equal to 1, then if load is equal to 1, then temp signal will receive the value num. That means whatever the input your input, that means the count, num is nothing but the count whether where you want to load, that you will save or that will store into this temporary signal. Else if this condition is not satisfied, then else if load is equal to 0 and direction is equal to 0, then temp will get receive temp plus 1. That means it will increment or it will add the 1 with that original value or original number. Because see here, we have already passes this num value to this temp value, and now we are increasing that temp. That means indirectly you are incrementing that num value by 1. We are incrementing that num value by 1. Else if load is 0 and direction is equal to 0, then temp will get temp minus 1, right? Temp will get temp minus 1. So this is how you can design a simply up and down counter simultaneously. Up and down counter simultaneously. So you just go through this code again. Once again, you just go through this code, and if you have any doubt, you can ask me. All of you are clear with this code? All of you are clear with this code?
Yes.
Okay, fine. Now we will discuss the last complex design, that is ALU, arithmetic and logical unit. Okay. Now what is the ALU, or what is the purpose of using ALU? What ALU does? What is, or what is the function of ALU? What is function of ALU, arithmetic and logical unit? Can anyone? What is function of ALU? It performs different arithmetic and logical operations, right? It is a what we can say, heart of the processor. Without ALU you cannot able to perform any arithmetic or logical operation. No, it is not possible. With the help of ALU only you can able to perform different mathematical and logical operations. So that is a function of ALU, to perform different mathematical and logical operations, right? Now, to perform any mathematical logical operation, how many input at least you require? फॉर एक्झाम्पल, तुम्हाला बेरीज करायची आहे, बेरीज करायला किती इनपुट पाहिजेत तुम्हाला? किमान 2 तरी पाहिजेत का नाही? कुणाची आणि कुणाची बेरीज करणार तुम्ही, बरोबर आहे? सो यू कॅन हॅव द 2 इनपुट, each input of 4 bit, input A and input B is of also 4 bit. Then now next question is, now there are different mathematical and logical operations, right? There are addition, there can be a subtraction, there can be a division, or if you consider the logical operations, there are ANDing, there can be a ORing, there can be a not of input, or A XOR B, A NAND B, A NOR B, anything, any logical operation you can perform. Now, for example, here we are considering this ALU has 2 inputs, A and B. Each input is of 4 bit. Then, depending upon the select operation, this ALU will perform the respective operation. That means, depending upon the select input, this ALU will perform the operation. That means, for example, if this select pin you have consider with the 0 0 0, right? If you have given the 0 0 0 input to this select pin, now in that case what happens? This ALU will perform the addition of this A and B. ALU will perform the addition of this A and B. Next, if you consider this 1 0 0 to the select input, that means if you have given this select input as a 1 0 0, then it will perform A and B. That means whatever the input you have given, it will simply perform the ANDing operation of that, and it will produce the output, right? So this is how arithmetic and logical unit works. Now we will discuss a simple VHDL code for this arithmetic and logical unit. Now this is a VHDL code for this ALU. So first we have defined the libraries, right? Library IEEE. In that IEEE we are using these 2 packages. First one is a standard logic 1164. In that all items we are using, and second package is numeric.std. This second package, in that package we are using also all items. So this is the library, this is the package, and this is the items in that package, right? So in this way we are using these 2 IEEE library and these 2 packages. Now next part is entity. Now by looking at the block diagram, how many input and how many output pins that we require? We require A, B input, and select is also input. So that's why we are defining here A as an input signed 3 down to 0, then B input signed 3 down to 0, and select input standard logic vector 2 down to 0. 2 down to 0. So these are the 3 input that we may require, and output is to get the or to receive the output. So this output is acted as a output port. So these are the entity. This is the entity for ALU, arithmetic and logical unit. Now next part is architecture part. So again we have used the process statement. So of course architecture is of behavioral style. So architecture behavioral of ALU is begin, then process A comma B comma select, begin. Now case select is means we have now instead of writing this select every time, we have defined this case statement which is a sequential. And now when 0 0 0, who 0 0 0, this select is 0 0 0, then output will receive A plus B. That means output will get value of addition of A and B. That means it will perform the addition operation. When 0 0 0, who is 0 0 0? This select pin is 0 0 0. Then this output will receive A minus B. That means it will receive the subtraction of A and B input, right? Similarly, when 010, that means this select pin is 010, then this output will receive A minus 1. That means it will simply subtract a 1 with input A and it will produce the output. Similarly, when 011, A plus 1. 101, it will simply AND the two inputs, that means A and B, and it will produce the output. 101, it will OR two inputs, that means A and B, it will produce the output. When 100, then it will simply produce a NOT of A. See, it is not a code. Okay, that means if 001, you have to give an A plus B only. It is not necessary. Here you can write this A and B also. Sequence you can change, right? For any select pin, what operation you want to perform or what operation you want to perform by the ALU, that you can decide. लक्षात येत आहे? म्हणजे या प्रत्येक सिक्वेन्सला हे ए प्लस 000 ला ए प्लस बीच असलं पाहिजे असं काही नाही. इथे तुम्ही ए अँड बी द्या, बरोबर आहे. 101 ला तुम्ही ए प्लस बी द्या. म्हणजे हा सिक्वेन्स काही फिक्स नाहीये. कुठल्या सिलेक्ट पिनला काय ऑपरेशन त्याने केलं पाहिजे हे तुम्ही डिसाईड करू शकता, बरोबर आहे. 0001 ला तुम्हाला ए ऑर बी करू वाटेल, तुम्ही इथं ए ऑर बी लिहा, डझंट मॅटर. म्हणजे काय ऑपरेशन परफॉर्म केलं पाहिजे ह्याचा सिक्वेन्स काही फिक्स नसतो, ते तुम्ही ठरवू शकता. म्हणजे 001 ला काय ऑपरेशन झालं पाहिजे हे तुम्ही ठरवू शकता, राईट. आय हॅव डिसाइडेड दिस ऑपरेशन. यू कॅन चेंज sequence of the operation, no problem. You can change for particular select input, you can assign different operation, no problem. या सिलेक्ट साठी तुम्ही इथं दुसरं ऑपरेशन पण देऊ शकता. असं काही नाही की ए प्लस बी दिलं पाहिजे. तुम्ही इथं ए अँड बी टाका, काही अडचण नाही. Clear with this? So this is, see, it's such a complex design. ALU is such a complex design, but with the help of this VHDL and EDA tool and all that, within a 15 to 20 lines, we are getting the 4-bit ALU with us. 4-bit ALU, that is arithmetic and logical unit. And if the same design, if you go for the manual designing, I don't know, you will get mad, right? I don't know how many days it will take to what we can say, get the output, and it will take to have that design. It will take to complete that design. We can't tell, but with the help of, within 3 minutes, you can write this simple code in VHDL and your design is ready for the arithmetic and logical unit. So this is what the what we can say worthiness of this EDA tool and VHDL language. Clear with this? Okay, we will stop here. I have discussed the enough examples of the combinational logic, sequential logic. It's how to write the VHDL code for the combinational logic and sequential logic. Okay. In next lecture, I will try to demonstrate you the actual use of that Xilinx ISC simulator and how to execute this same codes in that Xilinx simulator. Okay. I will demonstrate you some 1 or 2 example, and I will demonstrate you the execution process, execution procedure, and even how to simulate the output and how to verify the output. That will also demonstrate you in next lecture. Okay. So today we will stop here. So this is about the all theoretical expression, theoretical explanation of this sequential and combinational logics. So in all, we have studied the we have started from the very simple design, that is full adder, half adder. Then we have studied the comparator design, 3:8 decoder, flip flops, multiplexer, up down counter, then parallel 4-bit shift register, then parallel 4-bit parallel adder we have studied, ALU we have studied, right? So these are the some combinational as well as sequential logic designs we have studied up till now. Okay, if you want me to go for a few more examples, you can tell me what should I explain you, that I will explain in next lecture also. Okay, but I have covered the every complex as well as simple design of sequential logic and combinational logic. Okay. In next lecture, I will try to demonstrate you how to execute these VHDL code with the help of Xilinx ISC simulator. Okay. Today we will stop here. If you have any query or doubt, you can ask me right now. If you have any query, you can ask me.
No, sir.
Okay, fine. Then today we will stop here.